of materials into final shape and geometry, particularly those of metallic materials. And we are going to review fundamentals of this process and the things that we need to know as someone who has done materials and manufacturing unit. Well, indeed, casting and solidification processes are widely used in order to bring the materials, different types of materials into final shape and geometry, as I mentioned. And casting process can be used in order to shape not only metallic materials, but also some other materials as well. Like what? Like ceramics. What else? Polymers. And even composites. We can make use of casting process in order to actually bring components of different materials into final shape and geometry. And here in this picture, we can see a classification of solidification processes. And one of the most important categories within this classification is casting. Casting of mainly metallic materials, which is further divided or subdivided into some other groups, which we can say expendable mold castings and permanent mold casting. Two different methods. What's the difference between the two? The main difference between these two, expendable mold casting and also permanent. In expendable, say, mold casting, some sort of material is used which will be consumed, and we destroy the mold in order to make a part. In permanent molds, as the name indicates, mold is permanent, meaning that we don't destroy the mold in order to produce a part, and we can reuse it in order to make more and more parts. Did you want to ask something?
No, I thought you wanted us to comment on part one.
Yeah.
What is expendable?
That's what we're going to talk about. Indeed, in expendable mold castings, some sort of materials are used which cannot be reused, and they should be inexpensive. Like what? The material which is used in order to make the mold in expendable mold casting. The most common material which is used in order to make the mold is sand, silica sand. But also some other types of materials are used. Like what? Like clay sometimes, yes. Like what else? Plaster. What else? Ceramics even. Various types of materials are used. However, in permanent mold casting, often metallic dyes are used in order to produce the part. As it's a metallic mold, we should be able to open it up and to take the part which is inside the mold out of it. So it will be, there is a mechanism of closing and opening the mold system in order to take the produced part out of the cavity. Well, the whole mechanism, as explained down here, in casting of metals occurs in 3 steps. Step 1, melt the metal, pour it into, step 2, pour it into a mold, and then eventually let it freeze. Let it freeze. The whole mechanism is very simple. However, there is a lot of information and knowledge in this process, which we are going to make ourselves familiar with it. Why is casting an important process? A number of reasons are listed here. Casting can be used in order to make very complex and intricate shapes, which is really hard and time-consuming task if we want to make use of other processes to make the same shape and geometry. For example, machining. If we want to make use of machining process in order to manufacture a very complex and intricate shape. We need to spend a lot of time in order to cut the material and also to bring it to final shape and geometry. In casting process, it's made easy. So there is significantly lower time which is needed in order to make the part by making use of this process. The other thing is that we can make internal and external shapes in the part by making use of casting. What does this mean? It means that any part has an external shape, how it looks like from outside. What happens if there is a hole or another shape or cavity inside the part? It is still possible to make use of, say, some cores in order to make the holes and internal shapes in a cast part. Indeed, the part itself in casting process is called casting. Casting refers both to the process as well as the part itself which is produced in this process. And the other thing is that if we are, there is a problem with casting process, and the problem is that often the surface finish or the surface roughness of the part which is made in this process is rough. And also, geometric accuracy of the part is low. And this makes it actually necessary sometimes to machine the part or to subject the part which is produced in this method to subject it to some other processes which are called finishing processes in order to bring the surface of the part to a more desirable surface roughness or to increase the accuracy and dimensional accuracy of the part. One of the most important methods which is used as a complementary process on casting processes is machining. So you may see it very often in industry that a part is initially produced by making use of casting process, and eventually it is subjected to another process or a number of processes such as machining, coating, etc., in order to enhance its properties and to improve its dimensional accuracy. However, the amount of the machining will be significantly lower compared to the process to a process when we are making the whole part by making use of machining process only. By the way, the amount of the scrap which is produced will be significantly lower. So as a whole, a combination of casting and some other processes can lower the time of production and also can lower the time of production, the cost of production. And in casting process, sometimes we are able to make really, really big parts. Like what? Some parts which could weigh tons, even tens of tons, which isn't possible to make them by making use of any other process. For example, say compare it with machining. We don't have a machine which is able to machine a really big part, 10 meters long, 50 meters long. It's impossible. But by making use of the casting process, it is made possible. So these are a number of reasons telling us that casting is a really important process. Well, of course, for any process, including casting, there are some disadvantages and limitations, as listed here, which I'm not going to review this. The only one that I am going to actually mention is safety, which is of concern in casting process. Reason, the worker is making use of a molten material which is really hot. By the way, the atmosphere, the environment where casting process is in progress is poisonous. So there is safety hazard to the people who are working in that environment. And in some Modern casting, say, workshops, you might see that robots are these days being used instead of human workers in order to deal with this issue. Well, of course, by making use of the casting process, we can make really small and tiny parts as well as really big and bulky parts. On the small side of the parts which can be used, which are produced by making use of the casting process, we can refer to dental crowns, jewelry parts, etc., which are really, really small. Is there any one of you who is familiar with how jewelries are made? Jewelries, gold pieces. Anybody who is familiar with making gold pieces, earrings, whatever? Casting is a process which is widely used to make those stuff, right? Casting. And as I said, we can make really big parts. The engine block of your own car has been produced by making use of casting process. I have never heard of any engine block which has been produced by making use of any other process. The only process which is used in order to make it is casting. You see, it has got a bulky, it's bulky, it has got a very complex shape. So many curves, so many holes on it, and the most actually convenient method to make it is casting. Can we make it by making use of machining process, the engine block? Yes or no? The engine block, the whole engine block. Yes, we can. We can make use of machining. Why not? However, it's going to cost us a lot more. Yeah, it's going to cost you much more. So, and time is money, by the way. If you spend time, you've got to spend money to make it.
That's a common cost because that I'm aware that with engine blocks are put together, they actually make the engine block out of aluminium, and it's extruded aluminium. It's not cast, it's extruded.
Well, extruded aluminium, you mean it is injected into a mold? Well, it is still called a category of casting process. It's a permanent casting process. Where you can, die casting, where you can make the cavity and inject the molten material into the cavity. So when it is cooled down, it takes the final shape of the cavity. Yes?
What about powder metallurgy?
Powder metallurgy. It's a different process. It's not considered as a casting process, but it is very similar to.
As an alternate of casting?
Well, it is very expensive. Powder metallurgy is a very expensive method. So you can make use of it, of course, but often it is used in order to make very small size parts where we are in need of high geometrical accuracy, which is not the case for the body of for the engine block. Okay? It is possible, but it is very expensive. So there is no justification for making use of that process in order to produce engine blocks. Okay, moving on. Well, indeed, let me move on to this slide where we have the shape of the mold. As you see here, we can see two different types of molds which are used in casting processes. In A, we can see an open mold, meaning it's not the part which is being produced is not in a closed cavity. So you melt the material and pour it into the cavity. It's open. Leave it there for some time, and after some time, it is cooled down to room temperature. You can just take it off the mold. And the part takes the shape of the cavity, of course. What is here is often sand, which is also called mold, and there is a flask which is used in order to actually surround the mold, and it is called flask. Often it's a metallic material flask which is used in order to be used to contain the sand inside it. And in this one, which is In B, we have got another mold which is closed mold. And of course, this is of common use in industry. The majority of molds which are used in industry in casting process are closed molds. As you can see here, we have got sand which is tightly packed inside the flask. The sand which is used in this process actually is moist. And it is mixed with a type of binder in order to actually take the shape and maintain the shape of the cavity. And it has got two halves, upper half and lower half. The upper half is called cup, and the bottom half is called drag. And there is a parting line right here dividing the two halves into upper and lower halves. Well, this is the cavity which has the shape and geometry of the desired part. Of course, if there is an internal shape, we've got to make use of cores. Cores are also often made of sand. However, often a finer grade of sand is used in order to make the core. And you can place the core inside the mold as you can see it here. Well, we have got a down screw and the gate mechanism which provides the possibility of pouring the molten material from the top here into pouring cup. Then it leads the molten material into the cavity. And there is a riser here which is playing a very important role indeed. What's the role of the riser? Does anyone know? Yeah?
Because of the very extreme, the mold flow is very up and down, and then growing the mold. For this reason, put the riser.
Indeed.
The mold flow becomes slower.
You mean turbulence, right?
Yes.
If you are referring to turbulence, it's the pouring cup which is taking care of turbulence and lowers the turbulence as much as possible. That's why we have got the pouring cup here in order to lower the effect of the negative effect of turbulence when we are filling in the cavity. Indeed, that could also help. The riser could also help to lower the turbulence, but the most important role that it plays is something different. Yes?
It will add to the pressure to give the shape, proper shape, the mold, the air bubbles.
Okay, air bubbles. Let me explain a little bit more. Well, air bubbles somehow could be right. Indeed, we know that when material is molten, its volume increases. Is that right? When you molten the material, it will have a higher volume than when it was in solid state. Now we are filling in the cavity with a molten material, which is occupying a larger volume. Then what happens if the cavity is cooled down, if the material in the cavity is cooled down to room temperature and it freezes? What happens then? What we get is a shrink part which is different in geometry than the cavity. It will have a smaller size compared to the cavity, which is made in order to make it. Does this sound right? Okay. So, as a consequence, we've got to take into consideration that when we are making the cavity, we've got to make it slightly larger in order to compensate for the shrinkage. Right? By how much? It depends on the type of the material, specific heat energy and the properties of the material. And there is a table in the textbook telling you how much bigger you've got to make the cavity, which depends on the type of the material. Often, we've got to make it between 1 to 3% larger, the size of the cavity. We've got to make it between 1 to 3% larger. And there is a table, as I said in the text, telling you exactly how much you've got to make it bigger depending on the type of the material used. However, there is something else that we've got to take care of when we are dealing with casting process. And it is really important. What is it? Well, when material is being solidified, which part of the material is the first part which freezes? Which part of it? Outside. Reason, the outside boundary is the first section of the material which solidifies, leaving inside in the molten state. Okay? And when outside is taking shape, that shape remains in place to the end of the process, the outside boundary. Meaning that just the skin of the part or cavity has been solidified. However, material inside is still in molten state. And over the time, after some time, inside of the material will also solidify. So, what happens then? We've got the outside boundary, the skin, which forms the outside external shape of the material. Inside, we've got still molten material. After some time, inside of the material also solidifies. So what do we expect to see?
Stress in the material.
Well,
There'll be stress in the material.
we expect to see some bubbles or void spaces inside the part. Does that sound right? It happens. It happens. Because inside is still in molten state, when it solidifies, it occupies less space. And as a consequence, some void spaces or cavities are produced inside the material, which is desirable or undesirable? It's undesirable. We have produced a part which looks okay. When you cut it, you see that there are some bubbles inside, which will affect the performance and functionality of the part after it is produced. How can we deal with this problem then? We are not interested in having bubbles and void spaces inside the material. How do we deal with this? Yes? What's that? Tap.
Yeah,
It wouldn't help, would it?
not cut, one fixed level.
Well, even if bubbles, you can remove bubbles from inside, you've got to fill in those bubbles. And those void spaces should be filled in with molten material, right? And that's the play riser is playing. That's why we have got riser in place. That one, this cavity. What is it doing? It's been designed in a way that this cavity or this riser solidifies after the cavity, the solidification of the cavity is complete. Meaning that during the solidification process, if there are some void spaces produced inside the part, we have got molten material available here, and this will be sucked. This molten material will be sucked into the cavity to fill in the cavity. And then this material has solidified. After this, it's the riser which solidifies. And as a consequence, there could be some void spaces produced in the riser instead of the part, which is not important because we are not interested in what we produce here. It's the material, which is excess material. We are going to cut it from here and we are going to put this back into the furnace and to melt it down and reuse it. So it's not important if some void spaces are produced here. What we are not interested in is having some void spaces in the part itself. How does that sound?
Good.
Thanks for saying that. So the role of the riser is to help me with this, to provide molten material to fill in the void spaces produced in the part during solidification process. So something which is important to us as engineers, we've got to be sure that we have designed the cavity and the riser in a way that the riser solidifies after the part. Otherwise it won't work. If riser solidifies before the cavity, what happens? When cavity is in need of molten material, it's not available. And as a consequence, void spaces will be produced. How can we do this? That's something that we are going to talk about in this, say, lecture, in the remainder of this lecture. Okay, this is what we already had, so let's move on. Gating system. In the gating system, let me go back to the slide here. Gating system is referred to this bit of the, say, mark system. As you see, we've got Turing cup up here, and we've got down screw. Down screw has got a conical shape, as you see. It has got a conical shape. It has got a larger cross-sectional area on the top and a smaller at the bottom. Reason, this helps lower turbulence when we are filling in the cavity. And then molten material flows into the runner and gating mechanism. As you see, it's the runner which leads into the cavity and also into the riser. And we have got to design it in a way that the runner and the gating system has got a cross-sectional area which is sufficient for the process. Meaning what? Meaning that, suppose that if this part of the gating mechanism is solidified before this cavity and this cavity are solidified, what happens? This bit is solidifies before the cavity and also before the riser. We have got the still molten material here, but this section which connects these two bits to one another is solid. What happens? Exactly. Those cavities or bubbles inside the part cannot be filled in. So then we've got to design this bit of the gate mechanism in a way that it does not solidify before the tube. How do we deal with this? We've got to place these two cavities very close to one another in order to produce some heat, in order to keep this bit of the gating mechanism hot as long as there is a need to. The whole mechanism is called gating mechanism. And let's move on. Okay. And in order to melt a material, we've got to take the heat required in 3 different steps, which is listed here. The first bit of the heat which is needed is heat to raise the temperature of the material to melting point. Then we need heat of fusion to convert solid material into liquid material. When we have material has reached melting temperature, it is still solid, and there is a need for heat of fusion to change the state from solid to liquid. It consumes some energy in order to make that happen. And also, once material is molten, say for example, melting point of the material is 800 degrees C. If we just melt it and bring it to the process and we want to put it into the cavity, what happens? It solidifies before we can put it into the cavity. So you've got to elevate temperature to something above the melting point to compensate for this. So, number 3, heat to raise the molten metal to a desired temperature for cooling, which is often higher than the melting temperature of the material. Okay? Now let's do an example. Well, I have uploaded an equation sheet for this lecture, which you can find it on the blackboard. We have got, say, some 5 equations which are used in order to do the problems of this lecture. Let me quickly introduce the first equation. The first equation which you can see up here is the equation which is used to compute total heat required to raise the temperature of the molten material to the pouring temperature. And what we have got here is rho V, where rho is the density of the material, V is the volume which is to be filled in, and Tm stands for melting temperature, and TO is the initial temperature which has been used, which is often the room temperature we consider as 25 degrees if it is room temperature. And then we have got some specific heat energies. CS stands for weight specific heat for the solid material, and CL is the same specific heat energy when material is in the molten state. L stands for liquid. And then HF sitting right here is the heat of fusion, which is required to change the state of the material from solid to liquid. I think we have had some similar stuff in high school, talking about ice and water. Similar somehow. You remember that? If we want to convert a material, a liquid, if we want to make say some water freeze, we've got to apply 3 different actually energies in order to make that happen. We had this in the high school, right? Somehow casting process is similar to solidification of water, very similar. 3 different steps and 3 different, say, heat energies which are needed. Now let's go back to the lecture material. Okay, it's a very simple example. Let's see if we can do it ourselves by making use of this simple equation. If we want to have 1 cubic meter of a certain eutectic alloy, what does eutectic alloy mean now? Eutectic alloy, what does that mean? Eutectic metal. In eutectic metal, we will have either solid phase or liquid phase, where a 2-phase region does not exist. Material is either liquid or solid. We don't have a combination of the two at the same time. Okay? So eutectic means easily melting. It is like a pure metal. This is what we already know, right? Okay. So 1 cubic meter of a certain eutectic alloy is heated from room temperature to 100 degrees above its melting point. Now we know the reason. The alloy's density is given, melting point is given 800 degrees C, specific heat is given in the solid state, and that much for the liquid state. And heat of fusion is also given. How much heat energy must be added to accomplish the heating task, assuming no losses? We've got the equation, right? What is left? What is it? I didn't hear you. Just substitute those values in the equation. Simple as that. Okay? Doing it like that, this is what you get. Okay? It's a very simple process. Very simple process, similar to the one that we had in high school for ice and water, changing the state of the material from liquid to solid. This is what we already had, so it's very similar. Just substitute those values into the equation in order to compute the heat energy. However, please note that this is a simplified example. In practice, there is loss of heat in the process, which we have not considered here, to simplify the problem. And also, well, specific heat is different. Okay, everything else is fine. And as I said, TO for this given example has been considered as 25 degrees, which is the room temperature. Okay? Any questions on this? I have uploaded these problems on the Blackboard as a different file. Okay? If you don't have it in your lecture notes, then you can find it under a different, in a different file, which is example problems. Okay? There are 3 for this given lecture. For every lecture, it will be like that. It is uploaded, but I intentionally have not included them in your lecture notes. Reason, sometimes I want you to do the problem. If you have the solution with you, in front of you, many students will be reluctant in doing the problem. But if you don't have the solution with you, it makes you think and do the problem before you are exposed to the solution. That's the reason. Okay, let's move on. Well, another example. Example number 2. This is a little bit more challenging, still simple, but anyway, we've got to think before doing the problem. A mold sprue. Which part of the mold is sprue? The conical part. The conical part is called sprue or down sprue. A mold sprue is 20 meters long, which is the height of the sprue. 20 centimeters, sorry, not 20 meters. It will be really long then. 20 centimeters long, and the cross-sectional area of its base, when it is narrowest at the bottom, is 2.5 square centimeter. The sprue feeds a horizontal runner leading to a mold cavity whose volume is that much. We are after velocity of the molten metal at the base of the sprue. At the top, we will have a different speed compared to the base of the sprue. And volume rate of flow and time to fill the mold. These are the things that we've got to compute on the basis of the information that we have in the equation sheet. Let's take a look at the equation sheet, which I have also uploaded on my ECU on the blackboard. Well, read the equations also and the equation of the equations. And then try to see if you can do problem yourself before I expose the solution to you. Well, in equation 9.4, what we have is the velocity of the liquid at the base of the sprue. Isn't it what we are after? Is this what we are after? V. And in this equation, we've got G, which is the gravity constant, and we've got H, which is the height of the sprue, which is also given in the statement of the problem. Okay? Now, if this is the equation, if these are the three equations to be used for three different parts of the problem, are we able to compute what is requested in the problem? I'm showing you the equations to be used. Equation 1, I just explained what equation it is. In this equation here, where we have Q is the volume rate of flow. Where we have got V1 times A1. V1, there is a relationship between the speed of the molten material in the gating mechanism. There is a relationship between the speed and also the cross-sectional area of the gating mechanism at different spots. It looks familiar to us, right? This equation. Does it look familiar to us? Equation number 2. Familiar? Can you say another case where we have got similar equation? It's similar to what? Fluid flow. Fluid flow. Those who have done fluid mechanics, anyone of you who has done fluid mechanics? You have. Anyway, we make use of this equation to equate in fluid mechanics. The speed of the liquid in the gating mechanism at different positions has a relationship between its cross-sectional area. So if we have got a speed and cross-sectional area at one point in the gating mechanism, then we can, if we have the cross-sectional area of the other section in the gating mechanism, we can compute its velocity. And all of that is equal to Q, which is volume of the flow. And eventually time to fill in the mold is given in the very last equation. TMF, mold filling time, which has got a relationship with V. V is the volume of the cavity, and Q is what we have in the second equation. Okay? I have this at hand. It's not hard for us to do this problem. Okay, please go ahead and do the problem yourselves. A, B, and C by making use of the equation. I'm going to show you the result, so please do it yourselves to see if you can do it yourselves. The units, you can find the units here. In this equation, in this equation sheet, all the parameters and units are mentioned here. Well, because the statement of the problem is in centimeters, it's funny we do it in the same unit. As long as you mention the units, you're fine. Okay? Please do the problem, okay? If you don't do it now, you have to do it at home, okay? So why not do it now? We can do it for our next week. No problem. Papers.
No, the other page.
I can switch if you want.
Side. You can't put the side by side.
I am not sure if I can do it because it's a two different software. Okay, I can switch from one to another if you want me to. Okay. What's V? Are we done with first part of the problem? Speed? Yeah? What's that? Let's see. 198.1 centimeters per second is the speed of the sprue. Where is it? Let me show you in this figure here. We are talking about this speed, which is the sprue. The speed up here and bottom here will be different, and what we are after, we are going to compute the speed down here at the base of the sprue. Okay, that's what we are after, which is 198.1 centimeters per second if we substitute all these values into the equation. Right? G is given in the statement of the G is given, which is 981 centimeters per square second, and 20 centimeters is the height of the sprue, which is given. And 2 is of course given in the statement of the problem. Then we can easily compute V. This is centimeters, okay? So you compute it in a different unit, you will get a different value, of course. Part B. It's easy because we are provided with the cross-sectional area of the base of the bottom of the conical shape, which is that much, and A1, which is actually given to us as well, 198.1. Well, it's B, this is A. So if we multiply these two to one another, we compute the value of Q, which is question in part B, volume rate of the flow, which is that much. And then if we have the value of V, which is given in the statement of the problem, which is the volume of the cavity, that much. And we have computed Q in part B. So by making use of this equation, we can compute the time which is required to fill in the cavity, which is 3.2 seconds. Easy? Very easy. Okay? So we know, if we know which equation to be used, then it's not hard to do the problem. What's that?
It gets harder than this.
I beg your pardon? I'm not hearing you.
Harder than this.
Still don't hear you.
Or is this okay?
Say lower a little bit.
It gets harder than this, or is this as hardest it gets? Is the question.
I don't understand what you said today.
This is the hardest solution.
Can you make use of equations to make you understand? Give a word or something? Hardest in the exam. Could be a little bit harder. I got your question now. Could be slightly harder, but not really. I don't want to make you fail in the exam. Okay? I don't want to make you fail. I want to make you pass. Okay? But, well, could be a little bit more challenging. For example, next problem will be more similar to what you will see in the exam. Next example, which I'm going to show you, example 3. But anyway, this is the easiest problem to do. Just substitute values into the equation and get the number. It's very easy. However, still you need to know which equation to use. Okay? Okay, I'm leaving this bit to you. Okay, let's take a break for 10 minutes. Okay, there is another problem to be done after the break.